welcome to this lecture session of the course Engineering Thermodynamics. In the last lecture, we had discussed about the second law of thermodynamics. So we have come up with two statements for the second law of thermodynamics. One of the statement is related to the heat engine systems that we call as Kelvin-Planck statement, and the second statement, which is related to the refrigeration and heat pump devices, we call that statement as nothing but Clausius statement. Okay. Then I have shown you that both these statements are nothing but experimental ones. So we are not having any derivation of these statements from the first principle. Rather, these are derived from the numerous experiments which has been performed. Okay. And ultimately, we have also shown that for a process to happen, both the first law and second law of thermodynamics should be applicable. Okay, so if any of the law is violating, in that case, that process will not be practical. Okay. Apart from that, we have also seen that whatever the two statements we are having for the second law of thermodynamics, these are actually equivalent to each other. So it means if one of the statement is failing, other one will also fail automatically for the given system. Okay, so that we have seen by taking one example where our initially we have taken the assumption that Clausius statement is not applicable for a system, and we found that if we take any system for which Clausius statement is not applicable, automatically the Kelvin-Planck statement was also violating for that particular system. Okay. Now, in this equivalence only, let me take the reverse case that if I consider that initially my Kelvin-Planck statement is actually not applicable or it is violating. Okay. So let us consider a system for which Kelvin-Planck statement is actually violating. So though I have told you to try this by your own, but let me once again repeat it over here also. Okay. So if we are considering initially that Kelvin-Planck statement is not applicable, then what will happen to Clausius inequality for Clausius statement for that particular system? Okay. So once again, what I'll be doing, I'll be considering a source of temperature TH, and then I'll be considering a low temperature sink having say temperature TL. So this is my TH, which is greater than TL. Okay. Now I have to consider a system which violates the Kelvin-Planck statement. Okay. So let me consider over here one heat engine. So this heat engine is actually say operating in a cyclic fashion. Okay. And this heat engine, what it is doing, say it is taking QH amount of heat from the high temperature source, and say it is rejecting QL amount of heat, and QL is equal to 0. Okay, so if QL is equal to 0, in that case, obviously, this particular device, heat engine device, is actually exchanging the heat only with a single thermal reservoir, and it is say converting our entire amount of heat into work. So whatever the work we will be getting from it, that will be nothing but equal to QH. Okay. So this is the device which we have considered, which violates actually Kelvin-Planck statement. Now what we are doing, we are considering one more device over here, and let me say that this is nothing but my refrigerator. Okay. And this refrigerator is actually taking say QL amount of heat from the low temperature reservoir, and whatever the work this particular heat engine has done, the same amount of work actually we have supplied as input work to my refrigerator. Okay. So obviously what we will be finding, we will be finding that while refrigerator will be rejecting the heat to the high temperature source as per our law of conservation of energy, or from the first law of thermodynamics, we will be finding that amount of heat rejected will be nothing but QL plus W. Okay. And if I say that W is equal to QH from my heat engine, then I can directly say that it will be nothing but equal to QL plus QH. Okay. So this is the situation we have got. Now one important point I would like to highlight over here. If you see this particular high temperature reservoir, so this hot heat source over here, which is at temperature TH. So you can see over here in this TH, we are taking Q dot H amount of heat into the heat engine, and we are rejecting or we are adding some amount of heat QL plus QH into this high temperature source. Okay, so it means if I see the net amount of heat transfer which is associated with this hot temperature source, that is nothing but equal to QL. And what I can do from here, I can directly give this say QH amount of heat directly to my heat engine, and I can simply give QL amount of heat to this source. Okay, so that I can do over here. So let me draw this new system. So what will be happening? Our new system will be looking something like this. So this is my TH, and this is over here a sink with temperature TL. Then I have one heat engine over here. So this is my heat engine, which is producing work equal to QH. And then I have one refrigerator over here, and this refrigerator is actually taking QL amount of heat, and while it is rejecting the heat, it is rejecting nothing but QL plus QH. So now what we have done, we have transferred QH amount of heat over here. So from this particular heat, whatever we were obtaining over here, QH we have transferred to heat engine. So now the remaining heat over here is nothing but only QL. Okay. So now if you see in this particular system, between our two reservoirs, so temperature sources TH and TL, only our refrigerator device is actually connected. Okay. And if you see, overall this heat engine system is something, it is an internal system. Okay, so this is an part of the internal system over here, and this is actually taking this QH amount of heat and producing some work, and at the same point of time it is transferring heat QL to the from the low temperature source to high temperature, and this heat is actually being transferred without any work input from the surroundings. Okay, how? So if I consider this my entire thing as my part of the system, so if you see this entire thing is my part of the system, so in that case you can see that work is actually being produced within the system only. Okay, so that's why what is happening, we are getting a system which is transferring QL amount of heat from low temperature to high temperature without taking any external work. Okay, so it means this is nothing but the violation of Clausius statement. Okay, so it means it is the violation of our Clausius statement of second law of thermodynamics. So our initial assumption was that for this particular system, Kelvin-Planck statement was violating. So it means if Kelvin-Planck is violating, automatically my Clausius statement will also violate for that particular system. Okay, so this is what we have seen as the equivalence between the two statements of second law of thermodynamics. Okay, one important point I would like to once again emphasize, that for a system to work, for a system to undergo through some process, both the first and second law of thermodynamics should be applicable. Okay, if any of the law is violating for any system, it means that system will not, or that for any process, that process will not be actually practically possible. Okay, so this is one very important point. And one more thing, like we see from the second law of thermodynamics. So second law of thermodynamics is kind of a negative statement which specifically mention about the impossible situations. Okay, the situations which are not physically possible. Okay, so because of that, second law of thermodynamics also tells that perpetual motion machine is actually not possible. Okay, so let me just give you the idea of perpetual motion machine. So any machine which actually violates the laws of thermodynamics, that we refer to as nothing but perpetual motion machine. So we call the very first type of perpetual motion machine as PMM1. Okay, so PMM1 is a perpetual motion machine of first kind. Okay, so this is a machine which actually violates the first law of thermodynamics. So any machine which violates first law of thermodynamics, that machine we call as nothing but perpetual motion machine of first kind. Okay, so as per the first law of thermodynamics, we cannot create energy, we cannot destroy energy. However, energy can be converted from one form to another form. Okay, so now if we create some machine or if we develop some device which is actually creating energy, okay, so that particular kind of machine we will be calling as nothing but perpetual motion machine of first kind. So let me give you one example. So let us consider our conventional steam power plant system. So what we are having a boiler, and this boiler gives us the high pressure, high temperature steam. That high pressure, high temperature steam then expands through a turbine, and at the exit of the turbine, we will be finding the low pressure steam, low pressure, low temperature steam. Then over here, we will be having nothing but some condenser. Okay, so this condenser will be transferring our vapor phase into liquid phase, and at the end of the condenser, then we have to employ one more device which we call as nothing but our pump in order to increase the pressure. So this is nothing but a common cycle which is used in our steam thermal power plants. Okay, so in this cycle, what generally we do couple this turbine with some another device, and that device we call as nothing but our generator. Okay, so generator is a device which will be converting the mechanical energy into electrical energy, and then we will be getting actually electricity. Okay, so inside this boiler actually we add some QH amount of heat, and over here actually we reject some QL amount of heat. Okay, so now one of the important thing that we do in our steam power plants, we burn actually coal, and then whatever the energy is obtained from that coal, that we add in our boiler. Now let us consider that in this particular generator, from the generator we are getting some lines, and these lines are actually nothing but the electricity line. So this is my electricity which we are actually obtaining from the, so this is the electricity which we are obtaining from the generator. Okay, so now obviously in this pump we have to supply certain amount of work at the rate of W dot P, and this turbine will be doing the shaft work which ultimately we are transferring to the generator, and this is at the rate of W dot T. Okay, now what we want to do, let me say that instead of taking this heat from the coal, if I add some electric resistance heater. Okay, so what I am doing now, instead of taking the heat from the coal, so generally we have to add certain amount of heat in the boiler. So generally what we do in case of steam power plant, we add this QH amount of heat from the combustion of the coal. Okay, so now if we are saying that what we are doing, basically we are using over here electric resistance heater inside our boiler in order to heat or in order to create the high pressure, high temperature steam. Okay, so what I am doing, basically I am taking some electrical wire. I have one electrical resistance heater over here. So this is my resistance heater. Okay, and I am taking the electrical connections, and these electrical connections actually I am joining to nothing but my output, whatever we are obtaining from the generator. Okay, so this is the output which we are obtaining from the generator. Now what I am saying that this resistance heater, so we are producing some electricity, and part of that electricity we are actually employing for once again providing the heat inside the boiler, and remaining amount of electricity we are calling as nothing but W dot net. Okay, so now if you see in this particular machine what we are doing, so this Q dot H, whatever was earlier coming from outside, now we don't have this Q dot H, rather Q dot H is now being added from this electric resistance heating. Okay, so now you can see that if I consider that this whole is my thermodynamic system, if I consider this entire as the part of my thermodynamic system, so you can clearly see that we are not adding any amount of heat. Rather, whatever the heat is being produced, whatever the electricity is being produced within the system only, that electricity is only used to heat over here, provide the necessary heat inside the boiler, and at the same point of time, we are actually obtaining some net work output also. Okay, so this is something which is not possible because we cannot have a system which is actually creating some amount of energy without any addition of energy from outside. Okay, so this kind of machine which actually violates the first law of thermodynamics, this kind of machine is actually not practically possible, and this kind of machine we refer to as nothing but our PMM1. Okay, so perpetual motion machine of first kind. Similarly, we call one more perpetual motion machine, we call that as nothing but PMM2. So PMM2 is nothing but a machine which does not satisfy second law of thermodynamics. So if we are having a machine which does not satisfy the second law of thermodynamics, we call that machine as perpetual motion machine of second kind. Okay, so I can take once again the earlier example. So I'll be taking a boiler, and inside this boiler, say we are adding heat at the rate Q dot H, and then we have one turbine. Okay, and this turbine is actually doing some soft work at the rate of W dot T, and then what we are doing now, we are not taking condenser. Okay, so we are not rejecting any amount of heat. So if we are not taking condenser, so Q dot L will be equal to 0, and directly we are actually using the pump over here. We are directly using pump in order to compress our stream and supply over here. Okay, so this type of device, we are only exchanging the heat with a single thermal reservoir. That kind of system we call as nothing but our PMM2. Once again, we cannot have a system with Q dot L equal to 0. Why? That we will try to see in the subsequent lectures. Okay, but now if you see from the second law of thermodynamics point of view, this you are getting a system which is only exchanging the heat with single thermal reservoir. So it is a violation of second law of thermodynamics. So any machine which violates second law of thermodynamics, we call that as nothing but perpetual motion machine of second kind. And once again, this kind of machine is also not physically possible. Okay, so on the similar notes, we call one more machine as PMM3. So PMM3, we give the definition as a machine which run continuously. Okay, but this machine is having frictionless components. So there is no friction. Okay, so everywhere we are having actually frictionless components in this machine. So what it will be doing, though this machine will be running continuously, but it will work. So if we are having a machine, and inside this machine we are having all the components as nothing but the frictionless components, so obviously that machine will keep on running continuously because we are not having any friction or any resistance to the components of that particular machine. So that's why that machine, though it will be running continuously, but it will not produce any amount of work, because if we have to obtain some significant amount of output work, then obviously our system will be having certain resistance, and that system will be overcoming the resistance in order to produce some net output work. Okay, so if we are having a machine where we are not having any resistance, it's each and every component is actually subjected to the frictionless condition, and so in this particular case, what will be happening, though our machine will be running continuously, but it will not produce any amount of work. So this type of machine is referred to as PMM3. Okay, so though it is quite clear in the fundamentals of thermodynamics that it is not possible to obtain a physical machine which violates the laws of the thermodynamics, first and second laws of thermodynamics. So if we are having violation, then obviously that machine will not be working practically, but still there have been a number of attempts in order to create the perpetual motion machines, and even some of the inventors of the perpetual motion machines have raised significant amount of funding from the investors also to build their prototypes, but ultimately no one has succeeded till date to create a PMM. Okay, so one of the example just I would like to quote over here. So there was one carpenter, J.W. Kelly. So this guy has actually claimed that he has created a perpetual motion machine. So somewhere close to 1874 to 1898, he has claimed that he has created a perpetual motion machine, and the name of his machine was hydropneumatic pulsating vacuum engine. Okay, so this was the name of his machine, and he has claimed that with 1 kg of water, so if he take 1 kg of water, with that he can run a train for 3000 miles. So that was his claim, that with 1 kg of water he can run some engine, and that engine will be actually able to move a train for 3000 miles. Okay, so this was one of the perpetual motion machine which was actually presented very initially, but later on it was found that in his prototype he has used some hidden motor, and from that hidden motor actually he was producing the output work. Okay, so his claim was actually false. Okay, so that is how, like, many people, other people have also attempted to create some perpetual motion machines, and they have also raised some funds, but no one has succeeded yet to violate the laws of thermodynamics and to make some device which is actually practically possible. Okay, so now yes.
Sir, can you just explain perpetual motion to once again?
Okay. So in case of PMM2, what I have told you, that we are having once again the identical arrangement of boiler, turbine and pump. But from this particular cycle, this is identical to that of our steam power plant only. But in this particular cycle, what we have done, we have actually removed the condenser. So if we have removed the condenser, so amount of heat rejected is equal to 0. So it means over here, nothing but we are having only a single reservoir, and which is having temperature TH, and that is supplying the heat Q dot H amount of heat to our boiler, and because of that we have connected the components in such a fashion so that they are giving some net work output and operating in a cyclic fashion also by exchanging heat only with a single thermal reservoir, because Q dot L is equal to 0. Okay, so this is nothing but a violation of second law of thermodynamics. So why this kind of machine is not practically possible, that we will try to see in our subsequent lectures. But at the moment, from the laws of the thermodynamics, we can say that it violates the Kelvin-Planck statement. So because of that, this particular kind of machine will not be possible, and that's why it is referred to as perpetual motion machine of second kind. Okay.
Sir, does in the PMM1, PPM3 means resistance-less?
Yes, we are not having any friction, any resistance. So because of that, what will be means components are not having any resistance. I am not talking about over here electric resistance. Okay, so this is something different. Don't compare it with the electric resistance. I am saying that it is not having any external load which is acting on the system. So it is not having any resistance which is acting on the system. So because of that, it will be running continuously, but obviously because it is not moving against any external force or external resistance. So because of that, its work producing ability is 0. Okay.
Okay. Sir, in the PMM1 example,
can I take the doubts either at the end of the lecture or in the doubt clearing session? Okay, so that will be, I think, better. Okay, so now let me talk about another kind of very important process which we call as reversible process. Okay, and but before that, let me first explain that what is the need for reversibility. Okay, so from the second law of thermodynamics, particularly from Kelvin-Planck statement, we have come up with the idea that efficiency of an heat engine is nothing but equal to 1 minus Q2 dot by Q1 dot. Okay, And we have also seen that it is not possible to have q dot 2 is equal to 0. So if it is not possible to have q dot 2 equal to 0, it means our efficiency of heat engine has to be less than 100%. Okay, so that is something which we have seen from the second law of thermodynamics. Okay, but now we are having one unanswered question, and the question is that if efficiency of heat engine is less than 100%, then what is the maximum value of efficiency? Okay, so that is something which is still a open question for us. Okay, so what is the maximum value of efficiency for an heat engine, for a heat engine? So say if we are having a heat engine, from second law of thermodynamics, we are saying that its efficiency is not equal to 100%. Okay, so if its efficiency is not 100%, then what is the maximum value of its efficiency? So that is still an open question. So now I am not exactly going to answer this question in this particular lecture. Rather, what we will be doing, we will over here study a very specific kind of process, ideal process, and that particular process we call as reversible process. And this reversible process concept will be ultimately employed to define the maximum efficiency of a heat engine. Okay, so what we are doing, we are having open question that what is the maximum value of efficiency, which is coming from the second law of thermodynamics. So obviously, in this present lecture, we will not be able to find out its final answer, but over here we will be talking about some ideal process, and that ideal process will be actually known as or is particularly known as reversible process, and it will be helping us in defining the maximum value of efficiency of an engine. Okay, so let me first define that what is a reversible process. Okay, so let us try to see first the definition of reversible process. Okay, so a process, obviously if we are saying a process, so what will be happening, we will be having some state 1, thermodynamic state, and then we will be having change of state. So we will be having the occurrence of a process, and we will be finding some another thermodynamic state 2. Okay, now if we say that we are having a process which actually reverses its path. Okay, so it means it is changing from state number 2 to state number 1. And while it is reversing its path, it is not affecting the system and surroundings. Okay, so if it is not affecting system and surroundings, that particular kind of system we will be calling as nothing but our reversible system undergoing through reversible process. Okay, so if we are having a thermodynamic system which has gone through some process in which the change of thermodynamic state has happened. Okay, now if process returns to the initial state by following almost the same thermodynamics intermediate states in the reverse manner, and it does not affect the system and surroundings, so that particular system we will be calling, or that particular process we will be calling as nothing but a reversible process. Okay, so once again let me explain this concept with the help of an example. Okay, so if I take one example of a piston cylinder system, so I have a cylinder, and inside this I have a piston, and let me consider that inside we have some gaseous medium over here, and it is at some thermodynamic state 1, and we are having, say, a number of weights, small number of weights which are kept on this system. So now what I will be doing, one by one I will try to remove these weights. So if one by one I remove the weights, what will be happening? My piston will be slightly moving in upward direction. Okay, so you can see somewhere in intermediate state the location of the piston, and obviously at that point the number of weights on the piston will be actually now less. So whatever the initial number was there, now we will be having weights less in comparison to the initial number of the weights. So now if we continue this process, finally we will be finding that we are having a situation where our piston will reach to the highest position, and this entire chamber will be completely occupied by the gas, and obviously now we are not having any weight on the system. So corresponding to this, the thermodynamic state of the system will be changing, because over here we were having the significant weight on the system. So pressure of the system and volume of the system was very low and pressure was very high. So we were having state as thermodynamic state 1. And now for the second situation, what we will be having, we will be having some thermodynamic state 2, where our pressure is P2, which is less than P1, and volume is V2, which is greater than V1. Okay. So obviously, during this process, what has happened, if you see, the process has taken place from point thermodynamic state 1 to thermodynamic state 2, and because we were having a small number of weights, so we have slowly one by one removed the weights. So because of that, our piston has actually progressed gradually. Okay, and during this process, you will be finding that, let us consider that our system has done W amount of work. Okay, so obviously because this piston is expanding, boundary of the system is expanding against some external load which is created because of these weights. So over here we will be having some amount of work done, and obviously we are considering that our piston and cylinder arrangement is actually frictionless. So we are not having any friction in between the piston and the cylinder boundary. Okay, now if I have to reverse this situation, it means if I take that my state thermodynamic state 2 is initially known. Okay, and now I have the piston over here. Now what I am doing, one by one I have started putting the weights. So if one by one I am putting the weights, so because of that, what will be happening, I will be finding that now my piston will be moving downward, and we will be having certain weights now over the piston. Okay, so finally we will be finding that whatever the number of weights initially were there on the piston, if we are adding all the weights, so we will be having actually our thermodynamic state once again identical to that of the, so we will be having thermodynamic state once again identical to that of the thermodynamic state which we have taken initially. Okay, so something like that we will be having weights, and obviously our thermodynamic state over here will be state number 1. And what we are doing over here in this particular process, you can see clearly that we are adding the weights externally on the piston. So it means work is actually done on the system. So because of that, the amount of work transfer W 2 to 1, whatever we will be having, this is actually done on the system. So this much amount of work is done on the system. And if I see my previous slide, this W1 to 2 was work done by the system. Okay, so it means in this first case, what has happened, while the system has moved from state 1 to thermodynamic state 2, during that time, if I say this is my system and outside is my surrounding, so during this change of thermodynamic state from 1 to 2, this particular system has added the 1 to 2 W amount of work into my surroundings. Okay, so it means that during the process 1 to 2, system has suffered a loss of work equivalent to 1 W to 2, whereas surrounding has gained W1 to 2 amount of work. Okay, now if I see in my next slide, during the reverse situation, what has happened, this is my system. So system has changed the thermodynamic state from 2 to 1, and this is my surrounding. So now surrounding has added amount of work which is equal to W2 to 1, and the system has gained now work and the surrounding has loss of work. Now if we see over here, so what was happening, you can clearly see in this first situation, initially we were having all the total weights which were acting over the piston. Then while the piston has slowly moved, we have actually removed certain amount of weight. So we can say that whatever the external force was acting on the piston, this external force has gradually decreased. Okay. So in this first case, what has happened? F external, which was acting on the system, this F external has gradually decreased. Okay, so initially at the starting point, F external was high, more, and gradually, while we have kept on removing the weights, it has actually gradually decreased. Now, in this second situation, what has happened? Here, initially, you can see there is no weight, then we have put some weight, and slowly we have kept on adding the weights. So, it means in the second process, F external has actually gradually increased. So here F external has gradually increased. And moreover, we have considered that amount of these small weights is very small. So because of that, upon addition or removal of the weight, the displacement of the piston is actually very small and very slow. So it means our process has almost happened in nothing but a quasi-static fashion. Okay. So if process has happened in quasi-static fashion, so what we can do, I can draw it on the property diagram, say PV diagram. So initially this was the state, my state number 1, then this was my final state as state number 2, and then in between these two states we were having the number of intermediate thermodynamic states. Okay, so we were having number of intermediate thermodynamic states. Now, while the process will be reversing, obviously, because our process is quasi-static, so it will once again follow the same path. So during the reverse direction also, it will once again follow the same path, and it will pass through the same number of intermediate thermodynamic states. Okay, so once again, it will pass through the same number of intermediate thermodynamic states. So because of that, we will be finding that whatever the W122 amount of work we were having, that will be nothing but equal to minus W221 amount of work. Okay, so W122 was the work done by the system, and W221 is the work done on the system. Okay, so because the process has happened in quasi-static fashion, so because of that, what will be happening? Whatever the amount of work it has done during state from 1 to 2, the magnitude of that work will be equal during the work from 2 to 1 process. Okay, so now over here you can see that during the forward process from 1 to 2, system has suffered a loss of energy equivalent to 1 W2, and we have added some work to our surrounding. So while we have reversed this system, during the reversal, actually, the surrounding has suffered loss of work, and we have added equivalent amount of work into our system. Okay, so it means in this particular process, what we are doing in this particular process, while we are moving from 1 to 2 and once again from 2 to 1, during this entire thing, in our, if I talk about system first, it has loss of work minus W122, and during the reverse, it has actually received the equivalent of work, so plus W221, whereas their magnitude is same. And if I talk about surroundings, in terms of surroundings, we have actually now gain of work 1 to 2 during the forward process, and we are having actually loss of W221 during the reverse process. Okay, so it means ultimately, if you try to see, the magnitude is same, so we are not having any net work interaction between our system. So it means during the entire forward and the backward operation, net work interaction of system is actually 0. Similarly, the net work interaction of our surrounding is also 0. And in this particular case, we had considered that our system is actually having adiabatic boundary. So because of that, we have not considered any heat transfer. So it means our Q net for both system and surrounding was 0. So Q was also 0. So because of that, we can say that if a process is happening in forward manner and if we are just reversing the process also, and during this entire forward and reverse cycle, if system and surrounding are not having any net work and net heat interaction, we will be calling that our system and surroundings are not affected by the process. So because of that, we can call this particular process as nothing but a reversible process. Okay, so this is one very important point. You have to remember that our system and surroundings should not undergo through the net heat and net work interaction while we are considering the forward and reverse cycle of that particular process. Okay, now let me give you the another example. So in this another example, what I'll be saying, say I have once again the piston cylinder arrangement, and this piston is now locked with the help of some screw. Okay, and now what we are doing, say we are having some high pressure gas over here, and then now we are removing this screw. Okay, so while we will be removing this screw, obviously corresponding to initial point, we are having thermodynamic state as 1, and while we will be removing this screw, what will be happening, our piston will be rapidly moving till the highest position, and we will be finding that our system pressure has actually decreased and our volume has increased. So we have got new thermodynamic state as nothing but 2. And let us consider while this expansion has happened, during this our work transfer is say 1 to 2 W. Okay, so this is the amount of work which is done by the system. Now you can clearly see that during this entire process, while we have removed this particular screw, so because of that, piston has suddenly moved. So you will be finding that over our piston, the amount of force which was acting, so if I talk about external force which was acting on the piston, it was nothing but weight of the piston, mass of piston into G. As the mass of the piston is constant, so because of that, we will be saying that this external force will be a constant external force. Okay, because while our piston is expanding, only the weight of the piston is acting on the system. So while it is doing this 1 to 2, so W1 to 2 amount of work, that W1 to 2 amount of work is actually against this external force MP into G, which is actually constant. Okay, now if I have to reverse the process, so if I have to reverse the process, what will be happening? This will be my piston, and I have to, so this is my state number 2. Now I have to apply over here some amount of external force. Okay, so some external force I have to apply over here, and that external force will be actually moving our piston in the downward direction. So obviously we are supplying some external force, so it will be doing certain work on our system. Okay, so finally I will be finding that my piston will be reaching to some physical state where piston will be having gas inside, piston will be at its initial position, but we are having certain gas inside, and we have done a certain amount of work over here. So let me call that work as W221, and obviously that work has been done with the help of some external force XT. Okay, so over here what you will be finding, while we were having the piston at the topmost position, at that point we were having pressure as very small. Okay, while piston will be coming slightly down, so what we are basically doing, we are decreasing the volume, whereas amount of gas inside is same. So if we are decreasing the volume, so at the intermediate states, what will be happening? The amount of intermediate pressure will be actually increasing. As we will be moving further down, once again the amount of pressure will be more. So it means that during the compression process, whatever F external we are having during the compression process, so F external during this compression process, what we are having, this F external is not constant. Rather, this F external is actually gradually increasing. Okay, so over here you can see, because while we are compressing the gas, obviously piston will be having number of intermediate positions within the cylinder. So while we are reaching these number of intermediate states, in these particular states, what will be happening? My gas pressure will continuously keep on rising. Okay, so as the gas pressure will continuously keep on rising, so because of that, what will be happening? Whatever the amount of force which we require to compress that gas, that amount of force will be actually gradually increasing. Okay, so we will be having gradual increase in the force which we are subjecting against the piston in order to move it in the downward direction. Okay, so because of that, we will be finding that whatever the W221 amount of work we are having, obviously that work is done at the expense of F external, and F external has gradually increased in this particular second situation. So obviously whatever the amount of work W221 which we are supplying to this system, that will be more in comparison to the amount of work which we have actually got during the expansion process. Okay, so this is one very, very important point which you have to take care of carefully. Okay, so once again, I am just repeating this point. So during the expansion process, what is happening? During the expansion process, our external force which is acting on the piston, okay, so that was nothing but equal to MP into G, which is the weight of the piston. Okay, so our whatever the work is done, so this W122, whatever the work we have done, this work is done against the external force which was actually constant. Okay, and if we see the reverse situation, in case of reverse situation, what has happened? We have done some W221 amount of work, and it is done against some external force Fext during compression process, and this external force has actually gradually increased. So obviously the amount of force which we are supplying during the compression process, that is more. So because of that, the amount of work done which we are actually adding on the gaseous medium, that is more in comparison to the amount of work done which we have done during the expansion process. Okay, so because of that, what will be happening now? Whatever the gas we are having inside, this gas has actually taken more energy content. Okay, so during its expansion, it has given W122 amount of work, while it has received the work, that is actually W221. So because of that, its internal energy content will be more. So its internal energy content will be more, and this will be more by how much amount? This will be more by the amount W221 minus W122. So this is the additional amount by which we are having internal energy within our gas. So it means once again it has not reached to the initial thermodynamic state 1. So if we have to bring this one to initial thermodynamic state 1, what we have to do further? So physically our piston is at the bottommost position which earlier we were having, but the energy content of the gas is more. So in order to decrease the energy content of the gas, what we have to do? We have to remove certain amount of heat. So we are removing certain amount of heat Q. So because of or after removing that Q dot amount of heat, now what will be happening? Now we will be finding that finally when our internal energy content of the system is same, at that point we will stop our heat transfer process, and we will be finding that our system has actually reached to thermodynamic state number 1. Okay, so it means for this transformation from process number 2 to process number 1, what I have to do? I have done some amount of work W221, and at the same point of time I have rejected some Q amount of heat. So let me call this as also Q221. Okay, so once we are rejecting the heat, then only we are able to reach to initial state. Okay, so now let me represent these two situations. So first I am taking 1 to 2 transformation, and in the other side I am writing 2 to 1 transformation. Okay, so for the 1 to 2, this is my system and outside is my surroundings. So you can clearly see that during 1 to 2 process, we have only done W1 to 2 amount work. So this much amount of work system has added on the surroundings. Okay, and during the 2 to 1 process, if I see, this is my system and this is my surrounding. So what we have done during the 2 to 1 process, now we have added actually some work which is equal to W 2 to 1, and we have removed some amount of heat which is Q 2 to 1. Okay, so now overall if you see, our system has undergone through, during the 1 to 2 process, system has actually loss of amount of work W1 to 2 and surrounding has amount of gain of work as W1 to 2. However, during the reverse process, system has gained W2 to 1 amount of work and surrounding has suffered a loss of W2 to 1 amount of work. Okay, so in general, if I talk about W net loss we are having for surrounding. So W net loss for surrounding is nothing but equal to W 2 to 1 minus W 1 to 2. So this is the net loss of work which surrounding has suffered during this our entire cycle. Okay, and if I talk about heat, so in terms of heat, surrounding has actually gained some heat. So Q surrounding heat gain is actually Q 2 to 1. If I talk about system, so for the system we can say that W net system is nothing but equal to, so system has gained work. So how much gain of work we are having in the system? W 2 to 1 minus W 1 to 2. So this is the gain on the work of the system. And if we are talking about Q net system, so Q net system is actually as a loss because system has lost some amount of heat Q 2 to 1. Okay, so overall, if you compare, if you apply the energy balance, magnitude wise, you will be finding that overall energy content is balanced. Okay, so this is one very, very important point which I would like to highlight over here. So magnitude wise, if you try to see, magnitude wise, overall energy content of the system will be balanced, but overall energy content of the universe means system plus surrounding. So if I try to say over here, overall, if I include the system plus surroundings, the overall energy content including both system and surrounding magnitude wise will be balanced. But if I talk about quality, in terms of the quality, we are having actually different kind of energy which is taken out and different kind of energy which is added in. Okay, so it means in terms of the net amount of heat and work, we are not having complete balanced situation. Okay, so that is one very, very important point. Now what we are saying that quantitatively, magnitude wise, overall energy content of the universe which is comprising of the system and surrounding, that is same. But if we talk about quality of the energy, so our surrounding has suffered a loss of work, whereas it has obtained this much amount of heat. So it means it has surrounding. If I talk about, let me once again explain about the surrounding. So let me consider that this is my entire surrounding. So if I see in terms of surroundings, I have loss of work which is equivalent to W 2 to 1 minus W 1 to 2. So this much loss my surrounding has suffered. However, if I say equivalent magnitude Q 2 to 1, equivalent magnitude amount of heat gain our surrounding has suffered. Okay. So now if I have to make my surrounding unaffected, what I have to do? I have to convert this heat into work. Okay, so if I am able to convert this heat into the work, then obviously whatever this loss of work we are having in our surrounding, that will be actually compensated. Okay, but we know from our knowledge of thermodynamics, second law of thermodynamics, that complete amount of heat cannot be converted into work. So it means if I attempt also to convert this particular amount of heat into work into our surroundings, we will be able to get less work. Okay, so obviously if we employ some say external system to convert this much amount of heat into our surrounding, we will be able to do that. But the amount of work which we will be able to convert, that will be less in comparison to the amount of heat transfer we are having. Okay, so in total, if we say, if we are reversing this process over here, what will be happening? Our surrounding will suffer some loss of work. So if it is suffering the loss of work, because of that, we have to say that whatever the previous process I have taken, that process is nothing but an irreversible process. Okay, because one important point we have to remember over here, that our system and surroundings should gain or should have net amount of heat and work interaction. It means whatever the kind of energy it is surrounding is supplying to the system should supply same type of energy to our surroundings. Okay, the quality of the energy should also remain same. So because in this particular example, our quality of the energy is not remaining same, so because of that, we will be having overall some net heat and net work interactions while the forward and reverse process are happening. So because of that, we have to call this process as irreversible process. Okay, so now further discussion on reversible and irreversible processes I'll continue in our next lecture.